Welcome to the Deep Dive, the show that takes a stack of sources and really boils them down to the essentials, just for you. Today we're jumping into something that, sounds pretty technical, but trust me, it has huge implications for all of AI. We're talking about how we make those massive AI models, the ones driving the latest chatbots and everything, learn faster and, crucially, cheaper. I mean, think about it. Training these huge models takes an unbelievable amount of compute power. We're talking millions of GPU hours. It's just staggering. So any improvement, even something that looks small, can mean massive cost savings and really speed up innovation.
Exactly. And that's really our focus today. We're going to unpack a brand new optimizer called Dion, that's Dion, for distributed orthonormalization. And this isn't just, a minor tweak. It's specifically designed to tackle the huge scalability and efficiency problems you get when training these absolutely enormous models. So we'll guide you through it, kind of like exploring a really interesting academic paper. We'll look at the problem it solves, how it works, and what it all means.
Right. And our deep dive is mainly based on a recent 2025 paper by An and colleagues, but we're also looking at some of the foundational work that led up to Dion. So let's start right there. Why do we even need a better optimizer for these large language models? What's the core problem Dion is trying to fix?
Yeah, it really boils down to just one thing: scale. Sheer, unbelievable scale. Modern neural networks, especially LLMs, have just completely outgrown what you can do on a single GPU. It's not even close anymore. We're talking potentially trillion parameter models now. So to handle that, people use multiple kinds of parallelism all at once. Think of it like, building a massive skyscraper. You can't do it all from one spot. You need different crews, specialized equipment, all coordinated across the site. It's about distributing the work intelligently.
And that coordination is where it gets incredibly complex, isn't it? It's not just about adding more GPUs. You've got this intricate web of distributed computing. And the absolute top priorities are keeping those expensive GPUs busy and moving data around efficiently. But the optimizers we've been using for years, the algorithms that actually guide the learning, they just weren't built for this kind of massive distributed setup. They hit limitations.
They really do. Which brings us to this promising idea that came before Dion: orthonormal updates. Some recent work, particularly from Jordan and colleagues in 2024 with their muon optimizer, showed something really powerful. They found that using these orthonormal matrix updates could actually speed up training quite a bit, make it more stable, and even help transfer settings, hyperparameters, between different model sizes. So muon was really key. It proved the concept worked and had real benefits.
Okay, so muon showed the way, proved orthonormal updates were good, but there was a catch. A big one, it sounds like.
A huge one, yeah. Muon, while groundbreaking, had this really crippling bottleneck. It used a method called Newton-Schultz iteration. And the problem with that is it involves multiplying large, dense matrices together. Now, that's computationally heavy anyway, but the real issue comes in distributed training.
Ah, right. When a model is split up or sharded across lots of GPUs.
Exactly. When those parameters are sharded, Muon's approach basically forces you to either gather all the pieces back together on one device, which is slow and memory intensive, or it ends up doing a lot of redundant calculations on each shard. It's like having puzzle pieces in different rooms and needing to constantly bring them all back to one table to see how they fit, or having everyone work on the same section redundantly. There was this really striking anecdote. The Moonshot AI reference implementation of Muon, it would add over 278 days. Yes, days of extra optimizer compute time to a single training run for a model like Llama 3 405B.
Wow. Okay, 278 days just for the optimizer's overhead. That's completely unsustainable. It's not just expensive. It's a fundamental roadblock.
Absolutely. It's a massive obstacle. So that begs the question, right? Can we get the benefits of orthonormal updates without this insane communication and compute costs? Can we make it efficient for distributed systems?
And that's exactly what Dion sets out to do.
Yeah.
Okay, but before we dive into how Dion achieves that, maybe we should quickly touch on those parallelism techniques you mentioned. They seem pretty crucial to understanding the context here.
Good idea. Yeah, understanding these is key because they're the foundation that makes training these huge models even possible across many machines. Dion needs to work with them seamlessly.
Okay, so let's break down the main strategies. First up, data parallelism, or DP.
Right. Data parallelism, DP. In this setup, you actually replicate the entire model, all the weights, the optimizer state, onto every single GPU you're using. Then each GPU gets a different chunk, a different mini batch. of the training data. And after they each compute their updates, the gradients are averaged across all the GPUs, usually using something called an all-reduce operation. Think of it like students each reading a different chapter, then sharing notes so everyone learns the whole book.
Okay, so full model copy on each GPU, but different data. Makes sense for distributing the data load. What about FSDP, fully sharded data parallelism? Sounds like it tackles memory.
Exactly. FSDP is all about memory efficiency. Instead of copying the whole model everywhere, FSDP shards or slices up the model parameters, the gradients, and the optimizer states across all the devices. This massively cuts down the memory needed on any single GPU. The clever part is that a full layer of the model is only assembled or materialized right when it's needed for computation. Then it's immediately discarded, freeing up memory. It's like having only the specific tool you need on your workbench right now instead of the entire toolkit cluttering everything up.
Ah, I see. Much more memory friendly, which must be vital for those trillion parameter monsters.
Okay.
Okay, and the last one, tensor parallelism, TP.
Tensor parallelism, TP, tackles a different problem: computation within a single, very large layer. Here, the actual weight matrices, the tensors, within a layer are sliced up. So each GPU in a TP group only computes a fraction of the work for that single layer. The parameters, gradients, and optimizer states for that slice live permanently on their assigned GPUs within the TP group. This is essential when a single layer is so massive, it wouldn't even fit in one GPU's memory, or just to speed up the math. It's like having several people work on different parts of the same complex equation simultaneously.
Got it. So DP spreads the data, FSDP saves memory by sharding parameters, and TP splits up the computation within big layers. And you're saying Dion works smoothly with all three of these at the same time. That's what they call 3D parallelism.
That's right. It's designed to be compatible with this combination of DP, FSDP, and TP, which covers pretty much all the standard ways people scale up these massive training jobs today.
That's really impressive adaptability. Okay, so now let's get into the nuts and bolts of Dion itself. How does it pull off this efficient orthonormal update without muon's crippling overhead?
Okay, the core idea, the real innovation, is low-rank approximation. Instead of doing that heavy Newton-Schultz iteration on the full enormous matrices, Dion works with much smaller, approximated versions of those matrices. It orthogonalizes these smaller, low-rank matrices instead. Think of it like getting a really good executive summary of a huge report. You capture the most important information without needing every single detail. Dion does something similar with weight updates. It focuses on the most significant directions of change.
So it's working on a summary of the matrix, not the whole thing. How does it ensure that summary is actually good enough, that it doesn't lose critical information?
That's the clever part. It uses very efficient standard techniques like QR decomposition and sometimes Cholesky decomposition. These are well-known ways to break down matrices. But how it finds that low-rank approximation efficiently is key. It uses a method called power iteration. But crucially, it warm starts this process. It uses the result from the previous optimizer step as the starting point for the current step's calculation. This means even just one step of power iteration can give a remarkably accurate low-rank approximation, making it super fast.
That's the aha moment. It's building on the previous step's knowledge so it doesn't have to start from scratch each time. That makes sense. And the paper mentions ablation studies show this is basically as good as SVD's singular value decomposition, which is kind of the gold standard for accuracy in low-rank approximation, but known to be computationally very expensive.
Exactly. Getting SVD level quality, but much, much faster is a huge win. And there's another really interesting piece. Decoupled momentum buffers combined with an error feedback mechanism. Unlike older methods where you constantly have to synchronize gradients perfectly across all your data parallel replicas, Dion avoids that. Each device running a data parallel copy keeps its own local momentum buffer.
Okay, local momentum. But doesn't that risk the different model copies diverging? How does the error feedback fix that? Sounds critical.
It is absolutely critical. The error feedback mechanism is designed to compensate for precisely the information that isn't captured by that low-rank approximation. It cleverly reuses the momentum buffer itself to store and then reincorporate the error, the part of the update the low-rank step missed, into the next momentum calculation. This ensures that, mathematically, it ends up being equivalent to having done a fully synchronous global momentum update, but without all the communication cost. It preserves the optimization quality, especially when you're using lower ranks, meaning more aggressive approximation.
Wow. So even though it's approximating locally, the error feedback keeps everything on track globally, maintaining the quality. That's very clever. And because of all this, the low-rank approach, the efficient finding of it, The error feedback Dion can compute its orthonormal update without ever needing to gather a full parameter matrix onto one GPU. Which brings us back to its seamless fit with 3D parallelism DP FSDP DP. Just slots right in.
That's the beauty of it. Now, one important detail. This orthonormal update is specifically for the big matrix-shaped weights. Think attention matrices, MLP layers, and transformers. For other types of parameters like biases, embedding vectors, maybe layer normalization factors, Dion is designed to be paired with a separate, simpler, element-wise optimizer.
And the paper actually recommends a specific partner for this, doesn't it?
Yes, they recommend pairing Dion with Lion. Lion is another optimizer known for having a unit RMS update property, which basically means its updates have a consistent scale. This makes it a really stable and effective partner for Dion's matrix updates. So the Dion plus Lion combination is what they suggest for best results overall.
Okay, a hybrid approach. Makes sense. Now, you mentioned earlier that muon, and presumably Dion inheriting its properties, offered better hyperparameter transfer. This sounds like a huge practical win. Tell us more about that.
It really is a big deal for practitioners. Hyperparameter transferability means you can find the best settings, like learning rate for your optimizer on a smaller model or dataset, and then confidently use those same settings when you scale up to a much larger model without needing weeks of expensive retuning. Dion achieves this because its updates are inherently well-scaled. They're unit-normed due to the orthonormalization. Plus, it applies specific shape-dependent scaling factors to a single base learning rate. The upshot is, you can find one good learning rate, and it should work well across different model sizes, potentially even when combining Dion and Lion. It just massively simplifies the whole tuning process.
That saves so much guesswork and compute time. It's not just about raw speed. It's making the whole workflow more efficient. Okay, let's talk numbers. How does Dion stack up computationally against muon and, say, the standard Atom optimizer?
Right, the FLOP's floating point operations, basically how much raw math it needs. This is where Dion really distances itself from muon. For a typical matrix operation, muon's cost grows quite steeply, with terms involving the matrix dimensions squared and even cubed. Dion, even in a theoretical worst-case scenario with no approximation or sharding, significantly reduces those costs. It cuts the cubic term by more than 3x and the main quadratic term by about 25%.
That's a substantial reduction just baseline. And I assume when you factor in the low-rank approximation and the parallelism...
Like, it's much, much better. Exactly. When you use practical low-rank factors, say R being much smaller than the matrix dimensions, and you account for how things are sharded in FSDP and TP, Dion's computational advantage becomes significantly wider. It scales much more gracefully.
Okay, computation is down. What about communication? That's often the real killer in distributed training.
That's another big win for Dion. Its communication cost during the optimizer step primarily scales with that low-rank factor R, not with both large matrix dimensions ump and n like you might see elsewhere. So if R is small, the amount of data Dion needs to communicate between GPUs is drastically lower compared to Atom or muon. Less communication means less waiting, faster steps, lower costs. It's a huge benefit in large clusters.
Makes sense. Less data to shuttle around.
Yeah.
And memory. Always critical for these giant models.
Memory-wise, Dion is also quite efficient. Its total state requires storing the momentum buffer and a basis for the approximation, roughly M plus an R elements. One R is small. This is very close to muon's memory footprint, and importantly, it's never more than Atom's, which needs 2 element. Plus, like parameters and gradients, Dion state can also be sharded across FSDP and TP, further reducing the per GPU memory pressure, so it's competitive or better on memory too.
So less compute, less communication, efficient memory usage. The theory sounds great. How does this actually play out in practice? What do the experiments in the paper show for real training runs?
This is where it gets really exciting. The empirical results show Dion delivering substantial speedups. They found Dion consistently outperforms muon in wall clock time and achieves target validation losses 2 to 3 times faster than the widely used Atom W optimizer. This was demonstrated on a 3 billion parameter model, and importantly, they note the speedup gets even bigger as you go to larger models and use larger batch sizes.
Wow, 2 to 3 times faster training time to reach the same quality. That's transformative. That could literally cut months off development cycles for large models. How well does it scale with model size? Does it still work well with those aggressive low-rank approximations, like using only a fraction of the information?
Remarkably well. As they scaled models from around 120 million parameters up to 3 billion, Dion's performance, even using a very sparse rank fraction like R equals D16, so using only 116th of the rank, performed almost identically to full-rank muon. This is really significant because it suggests that these very efficient low-rank settings are perfectly viable for practical training of large LLMs, potentially even larger than 3 billion parameters. Using a smaller R directly translates to those compute and communication savings we talked about.
And what about batch size scaling? Sometimes optimizers get less stable with really large batches.
Dion seems to handle large batches very effectively. The results show it outperforming Muon as batch sizes increase, its critical batch size. The point where performance might start to degrade seems to be at least as large as Muon's, and potentially larger than Atom W's. Its ability to leverage large batches is key for throughput.
Okay, and how gracefully does it perform if you really push that rank fraction down? Does it fall off a cliff, or is it a smooth decline?
It shows a pretty smooth and predictable decline as the rank fraction gets smaller, which indicates it's robust. It remained very competitive with other methods like DEMO even at low ranks, and interestingly, it still beat Atom W even when using a rank fraction as low as 18. So it holds up well under sparsification.
And lastly, that hyperparameter transferability, did the experiments confirm that benefit?
They did. Figure 4 in the paper specifically shows that the optimal learning rates found for Dion were almost identical across all the different model sizes tested. This provides strong empirical evidence that it inherits that excellent hyperparameter transferability from Muon, which, again, is a huge practical plus for anyone training these models.
Okay, so Dion looks like a genuinely major step forward. Given how promising it is, where do the researchers see this going next? What are the future directions?
Well, one obvious area is quantization. That means exploring using lower precision numbers like 8-bit floats or even smaller formats for Dion's internal optimizer states, especially for parts like the column-normalized Q matrix. This could dramatically reduce the memory footprint even further and potentially speed up the calculations, especially on hardware designed for low-precision math.
Makes sense. Squeeze out even more efficiency. What about that error feedback mechanism?
Yeah, they think there's still room to refine that error feedback rule. Improving it could potentially lead to even better results at extremely low ranks, squeezing more performance out of even smaller approximations. The paper even mentions a variant called double Dion, which apparently shows promise in these extreme sparsity regimes. So pushing the boundaries of how much approximation is possible is definitely on the agenda.
Interesting. And while the focus now is clearly on LLMs, could these ideas apply elsewhere?
The authors suggest so. They argued that the core benefits of orthonormalized updates could apply to basically any neural network that uses matrix-shaped parameters and has dense activations. So while they tested on GPT models, you could potentially see similar speedups and stability improvements in computer vision, maybe speech recognition, or other areas where large matrix multiplications are central. The core principles seem quite general.
What a fascinating journey through this optimizer. So just to wrap up, Dion really feels like a significant advance for training large models. It's tackling the efficiency problem head-on with some very clever algorithmic design, the low-rank approximation, the warm starting, the error feedback, all while respecting the realities of distributed computing across DP, FSDP, and TP. It's not just faster, it seems smarter, scales better, makes tuning easier. It really could change the game for developing the next generation of AI.
Absolutely. It lowers the computational barrier, making it feasible to train models that might have been prohibitively expensive or slow just a short time ago.
So, thinking bigger picture, what does this mean for AI's future? When optimizers like Dion make training massive models more accessible, it's not just about incremental speedups. It potentially enables entirely new kinds of models, maybe ones we haven't even conceived of yet because they seemed computationally out of reach. What new capabilities might emerge? And it raises that classic question. Once you solve one bottleneck in this case, optimizer efficiency for orthonormal updates, what becomes the next major bottleneck? Is it getting enough high-quality data, the sheer energy cost, or just our ability to design even more complex architectures? It definitely gives you something to think about.
It certainly does. These technical leaps often have far-reaching consequences, opening up new questions and possibilities across the field.
Well, we hope this deep dive has given you a valuable shortcut to understanding this cutting-edge development in AI optimization. Thanks so much for joining us today.
Thanks for having me.
We look forward to bringing you the next deep dive.